Hello everyone, it's December the 11th, but we're doing the daily challenge for the 12th. Well, as I'm doing right now, I'm also publishing an app to the beta, to a staging area. So I feel like it's a wrong decision because I know the laptop is old and the streaming take a large chunk of the memory. So I'm not actually sure if it's going to go smooth for both the streaming and the publishing. But anyway, let's take a look. So I already opened two questions that I'm going to attempt. So the first one is for tomorrow's challenge, partition equals subset sum. So let's take a look what this one is about. Oh, I've done this before. See, I uploaded probably recent. I've done this recently. Ooh, look at that. Oh man, this is a hard question. Look, I started at 1 o'clock. Oh man, I think I remember this one. I didn't end until 4. It's like 3 hours. Oh, I seem to have remembered this one. Very frustrating. It's probably on my list. Yes, it's on my nightmare list. All right, let's see. After a year of practice, can we solve it now? Oh, I do not remember at all how this question is about. Given an empty array containing only positive integers, find if the array can be partitioned into two subsets such that the sum of the elements in both subsets is equal. Okay, so this is true because one subset is 155, the other is 11. This is false, the array cannot be partitioned into two equal subsets. Oh, first of all, I do not remember this question at all. And secondly, looking at this, I have no clue. I came back, it's like back to ground zero. Oof. Okay, so we want to partition this into two subsets with equal sum. I mean, an easy check is we check like this one, right? This one's 11, so it definitely cannot partition into 2. So that's an easy check to see if it's even or odd. And once this check is done, we can assume that it can be, like this one, we assume it can be. So the total is 22, the sum must be 11, right? The sum must be 11. Okay, so we can sort the array. Right, let's sort the array. 1, 5, 5, 11, right? And then we want to partition this into sum of 11. It has to be partitioned into 2, right? So 2 subsets, right? It has to be 2 subsets. Therefore, if I sort it into 1, 5, 5, 11, and I say I want the result to be 11, so we can actually see from the front 1. Well, we can actually see at the rear, right? So we have the value to get, which is 11, and we can go from the rear, and for this thing, the rear is 11 already, so it has to be by itself. So we can sum the remaining. Oh, it definitely works. If we can find, right, because we know the half, right? We know the half. So if we can find a subset that adds up to this value, then the remaining will work as well. So the question turns into finding a subset, any subset of the given numbers, such that their sum, they can sum up to our target value. Okay. So with this in mind, we can definitely run a DFS search, right? A backtracking search. So really, backtracking search. Yeah, like if I, you know, yeah, maybe it's easier to go from large to small. So let's say we sorted from large to small, right? In this case, it definitely works. But let's say it doesn't work, right? I mean, the half will definitely be larger than. So we will take the first one, okay? So we have something remaining, right? And then what? And then what we can do, because it's sorted, if anything that's larger than the remaining value, then we can skip, right? So we can we can binary search. We can binary search, right? So we take the largest one, and then we have a remaining value, right? So which means the remaining thing need to find this remaining value. And how do we find this remaining value? We can binary search it to find its upper bound. So okay, we find the upper bound, and then from the upper bound, we can say take the upper bound and a binary search again. Huh. Hmm. Doesn't feel efficient this way, right? I mean, we can binary search, and what if all the values are the same? I'm pretty sure the test case can be like 200 ones, something like that. But well, it definitely like the first one we said will definitely involve the last one, right? And then for the remaining, we need to search for a value that we can fit. And let's say, okay, so we binary search, so all the other cannot include. So binary search, so it turns into a smaller version problem. This is a little bit smaller with a new target. Because we know the largest value must be included, right? So I can just take away the largest value, then we have a smaller one, right? A smaller one. And then with the smaller one, then we have the remaining array with a target. Okay, so the question is, can we find a subset in this remaining anything, right? In this remaining that adds up to this target? Okay, how are you gonna solve that? And we just go, we'll take the first one, we need to find this one as target minus one, right? And we can take another one and all the way, and if it doesn't work, right? If it doesn't work with backtracking, try the next one. Well, if it's equal, we can actually, we'll try next one. Yeah, we try next one. And that is actually a combination. But length is 200, right? If it's 200, 200, I don't know, choose like 100. Oh, that's big. No. Nah, that's not gonna happen. Is there any efficient way to find a subset? I mean, we already shrank by, and now the question is whether those values. So we should take the bigger one. Like every time we take the bigger one. Okay, let's think about it. All right, we have an array, and we have a target. All right, now we take the big one, and then we have the smaller one. It doesn't solve because it could be all the value could be the same. Yeah, it could be the same. Hmm. Yeah, we take the first one and we what are the trick for this? Oh, let me think. Let me think. How about I mean counter will make things a little bit easier. So if we do counter, then everything is a single value, with a count, right? And we can still start from the bigger one. We just basically remove the bigger one, right? So big one is removed, and then we have the remaining value. But still it's a counter with a target. And how do we handle that? How do we know that the target can be formed by all these values? Well, I can say, I don't know, take as many small value as possible, and then try to find if I can fit the others. Okay, try to take as many as possible. Okay, take as many as possible, then we have a remainder, right? And then I try to see if the others can be used. Now we take as many as possible. If not, then I release one. Okay, then try it. If it doesn't work, then I release another one and try it. Once it's done, nothing works. Go back to the previous and I release one and try again. And this, maybe we can cache this. Right? It basically is the index to the end. So with this index given this value, okay, yeah, this we can cache. We can cache. We can cache. Hmm. And what's the difference between like from this from like one at a time, right? There's no difference. And it could be not include. Yeah, it could not even include this. Yeah, so there gotta be a way. If you take a look at the submission, like one of the method is like what 40 something milliseconds. So it's definitely 36 milliseconds, right? So definitely there is something that I'm missing, and I'm still missing after a year. I'm still missing. What is it? Can make it go so fast. Hmm. Yeah, the problem is just given an array, right? I want to see if if any element can add up to a certain value. That is the problem. Any combination can add to a certain value. and I don't know how many, right? That's another thing, I don't know how many. It feels to me to do this backtracking is, I don't know, it doesn't seem to be, I mean, backtracking is we start from the front, right? So we have multiple layers. The first layer is we start from the front, right? And then we can remove as much as we want. Okay, we remove as much, we take as much as we can, and then we take care of the rest. And then the front, we're gonna add one, add one, add one. And every time add one, we're gonna handle the remaining. Okay. And eventually, if the first one is not part of it, we're gonna go to the second one, right? And we can cache, but it feels like it's gonna take a lot of efforts. It'll take a lot of efforts, especially if one by one. But let's try this, right? I mean, we had this happen to us previously, that we think it's gonna be too slow, but eventually it's actually not. So I'm willing to try. Even though I actually don't know if it's gonna work. Well, still no good, huh? I cannot memorize. These things cannot be memorized. You memorize it, it's just not gonna work. So, all right, let's do this. Let's see if this one will work. The previous attempt we had what, like 4,000 milliseconds. So maybe it can work. All right, so we do need a counter. Need a counter. So to begin with, we are going to say counter. We're going to turn this whole thing into a counter, right? And then we're going to do uniques, right, equals sorted counter, right? So this gives us sorted the keys. And we're going to do sum. So it's called sum, right? So s equals sum nums. If s mod 2, then return false. Otherwise, target equals s divided by 2, right? And uniques is this, and then actually target we can handle it later. So unique is this, and then target equals s divided by 2 minus uniques last one, right? And then we say, and then counter uniques minus 1. We can do, no. Let's do it smarter. So max n equals max unknowns, right? And I say I'm gonna minus the max. So target minus max, and so max is this, target is this, and then we say counter max n minus equal 1. If not counter max n, I'm going to remove it. Right? If not counter max n, right? And we say del counter max n, and yeah, no end. Okay. So max n, I have a counter, I have max n, the target, maxing handle, and then we say uniques equals sorted count. All right, so this is the preparation work. All right, now the goal is to find target from any of the uniques multiplied by the counter. Okay, so now the problem is def, right? I can call it helper. We're going to pass in the index, which is the index of the uniques. So I'm passing the index for the uniques, and we're going to say current target, right? Yeah, it's the target. So the current target, and this one I'm going to cache it. So from func tools, import area cache. All right, so I'm going to cache this. And then this one I'm going to return a Boolean value if it's true or false. Okay, so given my current index, so what does it mean? This means whether, right, whether I can get a target by involving the current index. Okay, by involving the current index. All right, so I want to involve the current index. How do I involve? Say, doesn't matter, we can go small to big or big to small. I think it's the same, small to big or big to small. Yeah, if the current that this one does not, we cannot involve, then it's a moot point. Small or big, big to small is the same thing. But in that case, why do sort it, right? And you're not going to do any binary search. So I don't think I need to sort it. I think I just need to say uniques just equals num dot keys. All right, I want to put a list to it. All right, that's it. That's the uniques. There's no sorting, which is fine. I mean, if we can do it this way. Okay, so now I have the uniques. And now what? Now I want to say the index, all right, related to uniques. I want, say, whether the target can be achieved by including the current index, right? If it can achieve, then return true. If not, return false. Okay, so how many of this we need to include? So when I say for count in counter index, right? No, range 1 to this plus 1. That's how many we can include. So when I include C, right? What do? We say I'm going to include C amount. So we say if helper, right, index plus 1, and target minus C times uniques. Oh shoot, it's not index. This is going to be uniques index. So it's a current equals uniques index. Right. Oh, I do need that. So the current, right? C times current. If it's true, then I will return true. Right? Otherwise, we try the next one. We try the next one. If all tried, I will return false. Okay. So when is the last one and return true? It doesn't matter, right? I mean, if target is 0, right? If target is equal to 0, that's going to return true. Otherwise, we do this. Okay? So, with this in mind, we basically say, in the return, any, right? When for I in let's say for I underscore in enumerate uniques. Right. What I'm going to do is do helper I and target. We have a target. And any of this, if return true, then we return. Okay, we can actually test this, see if it works. So our test case will be this. This will return true. And this will return false. Yeah, of course this will return false. Okay, so we have nums and cam partition nums. Run it. All right, they pass, but you know, who knows? Let's try it. Yeah, we'll just submit it. That's fine. If it's not good, then it's just not good. I mean, 200. I expect this shall be. I don't know. If I pass, it will be pretty bad time. That's my guess. Runtime error. Ooh, what the heck? Oh, it's cannot do. Oh, yeah, for sure. I bet 125 shall return false, which just here, right? If index is equal to len uniques, then return false, right? Yeah. So add this line. I forgot to add this line. All right, try it again. Let's see. I got a wrong answer. All right, so this is different. Got a wrong answer. So answer shall be true, but mine gives false. Okay. So what's the sum? All right, in the print s target and the counter. Sum is 40. Target is 6. Yeah, target is 6. Yeah, target is 6. And then I try to find if it's target. So I also do uniques. Everything is 1, right? So uniques. All right. So the first one, I think it should be if target is smaller than 0, or this. Anyway, so it's still false. Okay. So 9 comes in, right? Current is 9. C, they're not going to do 1. So helper this. 6 minus 9 is minus 3. So return false. Right? So the first one return false. The second one, 8 comes in. Will return false because the charge is 6. Right? Target is 6. And then 4 comes in. 4 comes in. Okay, 4 comes in. And 2, right? 2. So 2. Oh, 2. Oh, I have to keep going. Gosh, dang it. I see. I see where this one's going. No good. So not only we need to consider the count, but this is also need to consider. So it's actually two levels, right? For j in range index plus 1, right? So it takes C, take index plus 1 all the way to len uniques. And then this one is not, we don't need this because I already handled it. And then we say if, I can just say if any, right, helper j target minus c times current for j in this. If any of this is true, then I'll return true, otherwise false. Ah, this is still not right. So j in range index plus 1. The current is the index, right? So from index plus 1, and I'm gonna do like 4 and 3 is bad. We're gonna do 4 and 2, right? 4 and 2. So coming in, that's 2, and I'm gonna use a 2, right? Use 1, 2. I want a helper 2 is index plus 1. Oh, 2 does not go. Ah, shoot. So you know what? Just to do it here, or index is equal to len uniques, right? And here we just say, I don't know, plus 1, because I want to take index. How do I handle this? So we have to do index plus 1, right? That's because otherwise the last one does not go. Now we pass, right? We have to go plus 1, okay? So what we're saying is I can do n equals len uniques. Okay, so we say if this is equal to n, or it's going to be n plus 1, so that we can make sure that we can j, if it's the last one, I can also take the next one. Okay, that's fine. And here I can just say for I in range n. Alright, let's try everything else. I'll pass. Alright. Back to here. I feel this one will time out. That's what I feel. Oh, did not time out. Alright. I'm surprised. I actually got this one. Okay. Well, is that an improvement from previous? Oh, so what type of solution was I looking for initially? take a look. Oh, and also I want to see this one's accepted. It's actually 83%. It's not that bad. I mean, like what I said earlier, right? You think it's not gonna work, but it actually will. I thought it's gonna be gonna time out. So this one, I backtrack. This is not backtrack. I'm trying to find this, but this one times out. Well, for one thing, I did not cache. Right, so I did not cache this thing. It's understandable. Same amount of test cases. And then did I try to cache the second one? Actually, I should see the last one. And that's when I gave up, I think. Or you can think about what's the difference between. Well, the difference, I don't know. Is there a difference? This is not going to happen, though. Right? This is not going to happen. Backtrack. I don't know. What was my last attempt? I'm trying to see like what's the difference between this way and the. I mean, for one thing, I'm looping this, so I'm gonna do one loop. But inside this loop, I still have to check different counts, right? I'm still checking different counts. I was using LEO cache, but it was still timing out. I mean, the one different thing is I minus the max value, right? I minus the max value, so I get it a little bit smaller. So the target is a little bit smaller, right? And also when I loop through, so it's not going to be every single value. It's going to be, because they are duplicates, so I'm looping through every single one. It's a unique ones. But as I'm going through the unique ones, I do check their counts, right? Do check their counts. So with this count, I'm trying to see if it fits. And then if it doesn't fit, I go to the next count. And the cache works in this one. How about this one? The target is 0, return true. If that's the same, right? That's the same, return false. And then I say include I plus 1. Or includes I plus 1. So like doesn't include this. Huh. Yeah, I don't know. This one just works. All right, let me first summarize this and then go through all the other solutions. All right, so 416. This was on my. This problem is on my nightmare list. Right, it's on my nightmare list. I first encountered it in November the 27th, 2020. And most likely and I first encountered and it took many hours to crack it. I was able to solve it this time in half an hour. So I think this counts as improvement. Anyway, so the idea this time is that we first check even or odd, and then we turn nums, and then we find the max value in nums and remove it from the target. If that we first check the sum of nums, right? If the sum is odd, we can return false immediately. Otherwise, we obtain the target sum divided by 2. Then we find the max value in nums, right? If the partition is successful, then the max value must be included in the target. By removing the max value from the target, we can shrink. We can make the problem. We can make the problem simpler. Thus, our new target is sum divided by 2 minus max num. Alright, divided by max num. Then we create a actually this is not necessary, because the uniques, no, it is. Then we create a counter for all the for nums and remove one count of the max sum. We then create an array from the counter a unique called uniques, right? Called uniques. Next, we perform recursion. The helper function. So helper index target returns true if it is possible, right? If it is possible that that some combinations of uniques index, right, including uniques index, some common can sum up to target. Thus, our result is helper 0 and sum divided by 2 minus max nums. Actually, I, where I equals 0, 1, 2, da da da, len uniques minus 1. The helper function, right, needs to go through all the counts for the current value and go through all the remaining indices in uniques. This one I do not know the runtime. What's the runtime? Well, worst case scenario, right? Worst case scenario, what's this gonna run? We run one count, and then we check the remaining. This one has to be one count. I don't know. Each index will be hit once, but each target is different. So I don't know. I don't know the run. I don't know the time complexity. I don't know. But we did run this in 342 milliseconds, or 83%. All right, so that's what we have now. Let's see, is this the one I pass? Yeah, this is the one I pass. It's a memo. All right, let's go directly to the good one. Okay, target is sorted. This must be included no matter what. Yeah, that's true. Temp equals this. J in target I to the n. Temp plus this. If temp is larger, as O(n) squared. This is O(n) squared. If temp is larger than target, temp minus this. If temp equals target, it's true. Okay. So for every I, right? For every I, we try J. Huh? No, for I from 1 to the end. For J from I to the end. Temp plus this. And if temp is larger than target, then I remove nums J. And I go back up. And I'm sorted. So every time if I add it, it's too big. But if I add it, that's small, then I keep adding the next one. Keep adding the next one. Until it's too big, then I remove it. And then I keep adding, right? So what is this way of thinking? We'll always, this is greedy, right? This feels greedy to me. The largest one, we realized that too this time, the largest one would definitely be included. And then I think it's just, because we go from large to small, we say, do we include the large one? Well, if we include the large one, it's going to blow up. Then we definitely don't include the large one, right? We just don't include the large one. And then we try the largest one that will not break. Okay, we try that one that does not break. And then what? And then we try the next largest one that does not break. Okay, then everything then is no good. So basically every step we try the biggest value that we can fit, and if it's good, then it's good. If it's no good, we come back to I move forward. So we try that one is the largest one. Huh. So I think this means each iteration of I, we are saying whether this value, whether this big value, what this value can be included, right? So to include this value, we can skip all the values that's too big, right? We skip all the values that is too big and find something smaller, then we try it. And then we keep going, and if it's too big, we just skip, 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 and I'll pick up something else. But what if this one shall not be? Right? How is this considering all the possible solutions? 10 plus equal to nums. So we're adding this num. Right? And after I add this num, the j just keep going forward. What if the actual solution does not include in this? Yeah, what if the actual solution does not include this j, but include, let's say, if we do this, and then, yeah, what if I need 4, and then currently I'm at 3, and I add 3, then I need 1, but there's no 1, but I do have 2 2s, right? In that case, what are we going to do? Temp plus this, and if it's smaller, then j keep going. Now I'm too large. So I remove. Try it again, too large. And then remove. Um, I I don't know. I remove, and I come back. I temp as this, and I go for 2. Oh, so hold on. What's objection? My objection is if I include 1. All right, because it's sorted, so they are all lined up, right? They're all lined up. So basically, each I we're asking whether this value will be included, right? So we add 1, and we can try add another 1. We add another 1, and then we cannot add, right? Cannot add, and then add something smaller. And if something smaller cannot add, so my question is, what if I can just remove one of this, and then I can fit in the remaining? I don't know. This is interesting. What was the thought behind this? I cannot see it. I actually want to see how my reasoning was back then. think it's 11, 1127, I believe. I didn't really elaborate. Yeah, I don't know. Why does greed, like, always adding the big one will work? But always adding the big one. And we know the big ones, they definitely need to be in there, right? My question is, when I do this, I'm not taking care of all the combinations. I can keep adding a value. Right, let's say allow me to do 2 3s. How about 3 3 and 2 2? 3 3 2 2 is, that's 6, that's 10, right? And I say, yeah, what if I have 3 3 2 2? Well, I have three. What if I have 3 3 3 and 2 2? And now the target is going to be 10. So I'll add 3, and which is good. So I keep adding the next 3. That's 6, which is good. Like 6 is smaller than 10. So I add another 3. 10 plus 9 is still good. Now I try to add 2, 11. We break out. So 10 minus 2. So 10 plus is still 9. So go up. We're going to add another 2. So go up. And then it will come out. Right? So 3. So how does this one work? I have this, right? And the target is 10. And we need to figure out a test case for this. This is 9. This is 4. That is 13. And I want at this stage target be 9. That target be 10. Now it's 13, so I need a 7, right? So I need a 7. Okay, 7 3 3 2 2. Let me try this. So I say 7 7 3 3 3 2 and 2. This one should be true. I have a pass. What? How? How? It's sort of reverse, right? And 10 plus 7. Oh, 7 plus 3 already done. Oh, maybe that's the reason. Hold on. Well, what's your objection? Well, my objection is it doesn't give a full. Yeah, my objection is it doesn't give a full. But it seems like it doesn't have to, right? So target is 10, and 10 minus 7 is 3. Huh. And I immediately find it already. Now it should be, we need to find 10 in this. Alright, so after removing the largest one, and we need to find a 10 in the remaining. So, and this gives us 13. Oh, this is a large value. I want the remaining to be 10. If this is 10, then we have 3 left, right? Whatever is left. Let me think again. Try to find this, right? And if it doesn't work, we always try the large one. And we try the large thing, and we try the large again. And then we try the large again. But that's not a problem. The problem is, before we try the second large, the problem is already solved. Okay, that's the remaining value. Basically, the large one is involved, the large one is not involved. But if it's involved, then like how many it's involved? It's involved 1, or maybe involved 2. Hold on. If the large value, if I don't get the most large values for each one, let's say I only get a small amount, right? If I get a small amount and I find the solution, what does that mean? If I don't take the full, I take this and say I find a solution. If that is the case, if I find a solution this way, I mean, hold on, by including, if I find a solution this way, that means the remaining plus this is also the same sum, right? Which is including this. This means hold on. Do it again. We have the large value, and then we minus large value, we say, well, okay, the remaining we need to find sum up to this, right? Sum up to the target. Sum up the target. If we sum up the target, then we're good. Okay? So we need to sum of the target, and if we keep doing this, it's not going to sum up the target. This equals this. Right? So we need to find something that can add up to the target. and I take in the big values. And we say one big value and try to check, right? We try to add as many big values as possible. I don't know. I got stuck. I don't know why this solution works. Knapsack. A knapsack. Several numbers in a set which are able to sum to a specific value. It's a knapsack problem. We can pick it or not. A specific sum j can be gotten from the first I numbers. If we can pick such a series of numbers, each number we don't pick it, which means if the fastest element has to make it to j, but also make it to j. Now numbers I and transition function is okay. What's DP again? Whether the specific sum j, whether the sum j can be gotten from the first I numbers. Okay. We can pick such a series of numbers from 0 to I, the sum is j, is true. Okay, 0, 0 is true. The 0 number consists of sum 0. And for each ij, I can say whether I pick I or not pick I. If we don't pick I, then that's equal to this. If I pick I, right, if I pick I, then because I have the ij, so just j minus nums I, right, that's the j minus nums I, that's the previous, like, because I pick I, so I need to know, without picking I, what the value can be is j minus this, right? And we want to know if the previous one, I minus 1, to I minus 1, if it's successful. So that is correct. So I just go ahead and do it. Yeah, so dpij equals this. If j is larger or equal to nums I minus 1. So this is not picking I. And j is the sum. So if the current j is larger or equal to the previous, that means I can include, hold on, that is not right. This is the nums I. This is the nums I minus 1. What is this about? Say, I want to know dpij, whether j, this value, can be formed from 0 to I. So if I don't pick I, then I need to check. So I don't pick I, so it has to be I minus 1, yes. If I do pick I, then we need to check is if j is larger or equal to it shouldn't be larger or equal to nums I, not nums I minus 1. Right? I think this should be nums I. Oh, hold on. Something is different. Okay, this one already equals this, so that's actually fine. So dpi minus 1. So it's j minus nums I. A 1D array. 1D array, let me think. I minus 1. We created 2 arrays. What is this magic? Okay, this is true. So for j, for the current j, right? The current j, I go through everything. I basically don't worry about I. Yeah, there's nothing because I minus 1 is a row, right? So we're always looking for the row above us. But I already updated the value. How can I? Hold on, let me try this one. I actually like this one better than this. It's a knapsack problem. Either take it or not take it. It is a knapsack problem. Use knapsack problem solution. Reference. Yeah, I completely didn't think about knapsack. dpij represents whether it is possible to sum up to j from any combination, any number combinations from any number combinations in nums 0 to I. Oh, 0 to I. I is not included. I think now we know why. Okay, sum s equals to sum nums. Right, I'm going to say dp will equal to 0 times s plus 1. Right, and for this in range len nums, probably do n. That's len nums. So range n. Yes. Okay. Then from 0 to I, not inclusive. So what if it's 0? I is 0. So I is 0 will be 0. Right? I is 1. Hold on. Does I include or not include? No, I want to include, so it's actually I plus 1. So therefore, I think we should add another one, right? So now I'm going to go from 0, right? So for I is 0, and then j going to be from 1 to the end, and let's say 1 to the end. It's not going to be this. It's going to be false. Everything will be false. And yeah, the thing is I minus 1, right? That's when I'm going to have issues. What's I minus 1? Yeah, so it's up to I, up to position I, right? Up to position I. So j is 0. Well, j will not be 0. Well, j will be 0. If j is 0, right, they need to sum up to j. That should all be true, right? Because if j is 0, we say any combination, we just can do no combination. Okay, if j is 0, it should be true. If I is 0, I is 0 is up to that value, right? Up to I equal to 0. Now, if up to I equal to 0 is the first value. So that, if it's equal to, then we're going to return true. But why do we need to handle this? Well, because when we do j minus something, right? J minus something can be 0. That should be true. We can also have I minus 1, right? So I minus 1 we need to know. So, okay, so we're going to say for I in range n plus 1, right? Say dp I 0. They'll all be true. Actually, except for 0. Wait, why except for 0? They are true. If j is 0, right, they will all be true. Yeah, so I think this is all true, right? Now, I still don't think it's n plus 1. No, it's not n plus 1. I think it's n. So for j in range s plus 1. That makes sense. Actually, we handle this actually from 1 to this. We say dp 0 j will equal to num 0 is equal to j, right? If it's equal to j, then we say we can use, yeah, okay? Then we say for I in range, well, 1 to n, right? Because I handled the 0 condition already. And then for each of this position, I'm going to go for j in range also 1 to s plus 1, right? So we need to find dpij. What's dpij? dpij is whether we can fix j given from 0 to I, right? From 0 to I. So we say it can either be, right? Okay, so dp I minus 1j. So this is not taking nums I, right? If nums I, we do not take it, right? If we do not take it, then it's I minus 1 j. So if I do not take I, then up to I position, whether it can form or not form is related to I minus 1. Yes. Now we say we want to take, but it has to be if j, hold on, how do I know if I can take it? If I can take the current value. So if j is larger or equal to the current value, which is dpi, and nums I, right? If it's larger than, then I say I can take it, right? So we say dpij equal to or equal to, so I'm going to take it, right? So if I am taking nums, then we're going to find the previous into the previous, right, to I minus 1, if it's possible to go j minus nums I. So this is taking nums I, right? And once it's done, we're going to return dp, which basically we say we want to find s if it can be taken up into I, the last one, if it's possible. Okay, solution 2. It's not right. Let's compare it to this. So I is true, and this is all false. Why? I have a couple of differences. But why is that false? Zero number consists of some 0. Oh, its I is the number. My I is the indices. Oh, that's not I. Come on, man. That's not I. That shall be n minus 1. They're still not right. N minus 1 is still not right. I have a lot of, hold on, let me think. Whether it's possible to sum up to j from any combinations in numbers 0 to I, right? That's our premise. To sum up to 0, do we have, I say, to sum up to 0, I say it's true to sum up to 0. Right? To sum up to 0 is true because The sum to 0, basically we just don't take anything. Okay. Now this in my case is we take the first, right? We take the first, and then we say we want to sum up to j. Now, if nums is 0 and equal to j, then we need to say it's true. Otherwise, we say it's false. Let's try this out. So we have 0, 1, 2, right? And the sum is 8. 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6, 7. 1, 0, 1, 2, 3, 4, 5, 6, 7. Do you need another one? Okay. So we say when j is 0, everything's 1. I say when I is 0, it depends. So we have 1, 2, 5, 1, 2, 3, 4, 5, 6, 7, 8. And we say I is 0, so I equal 1. So this is 1, right? Basically, I say, can I make 1 from 0? From 0? Yes, I can make 1 from 0. But all the others, can I make 2 from 0? That's false. So all the other is false. Okay. Now I from 1 to n, j from also 1 to s. So dpij. So we say we want to make 1 from 0 and 1, if it's possible. Make 1 from 0 to 1. Yes, it's possible, right? It can be I minus 1 this, and j is 1. Is it larger to nums I, nums 1? No. So this actually is possible, right? It's possible because I can just take 1. I don't have to take 2. Okay. So that's 2. Okay, so 0, 1 will make 2. So it's impossible if I don't take. Okay, now is it possible if I take nums 1, which is 2? So if I take 2, right, now we do j is 2. 2 minus 2 is 0. Right, so we can go back to 0, 0 is 1. That's true. Yeah, so that's true. Okay. 3. J is 3. So it's nothing. 3 minus 2. 3 minus 2 is 1. So we're going to do 0, 1. That's also possible, right? 4 minus 2 is 2. So all the others are not possible. Now we'll go to I equals 2. Okay, I equals 2. So now it's 1. The current, right? So J is 1. And dp, we're looking at dp 2, right? 2, 1. So 2, 1, if we don't include it, that's going to be true. So, and then j actually not larger, so that's true. This is current 5. So they're all true all the way to 3, right? All the way to 3 are all true.